In this lecture, Visualization Design Principles, we're going to look at some of the heuristics that you can follow in order to come up with good visualizations. Okay, so this is the final lecture for the course. It's relatively shorter compared to 187 slides. This is only 40 slides or something. So my so it's let's see how long it will take, about an hour, maybe 50 minutes to an hour or so, but I think it is also an important lecture, because even if you have not learnt some of the theoretical foundations in the previous lecture inputs, this is a set of heuristics that very easy to follow, right? So as designers, we are very familiar. Okay, I didn't even check with these guys. Are you okay? Yeah, okay. So as designers, we are very familiar with heuristics, right? So we rely a lot on heuristics that comes with trial and error, and then over a period of experience, we know what things work in which context, and then we try to apply it. If it doesn't work, then we kind of iterate it a little bit, try something different, and then iterate a little bit until we are satisfied with it, right? So design as an endeavor, it does not lead to very predictable outcomes, right? And it's not like science where there is one correct outcome, right? There are multiple optimum outcomes that you can think of, and everything is very closely tied to the context, and therefore it is very important, right? So one good definition of design is that it is the solution. Design solution is that it is just a set of arguments, for and against some issues, right? And then you resolve them by answering these questions, and sometimes you may not be able to answer all of the questions, but at some point of time you're satisfied with the outcome, and then you say, this is it, right? The project is done now, let's move on to the next project, right? So that's how heuristics come about. So it is just kind of shortcuts to doing something, and heuristics most of the time work because it is established over a long period of practice, right? For anything that is practical in nature, right? Any field that is practical in, like medical profession, right? The clinical medical profession is also relies on a lot of heuristics, right? Because doctors accumulate this knowledge and then have these heuristics for dealing with various situations, for certain context of patients and so on, right? So think of them as heuristics, okay? They are not rules, okay? And therefore you have to be very careful when you apply them. And these heuristics are very well articulated by Tufte. I already told you about him. He's written these 3 very important books. I think you all should read it. I actually own all of them, and they're kind of expensive books, so I kind of collected it over a period of time whenever I could afford them. But they are really the kind of books that you should be happy to display in a designer's shelf. Okay, so these are 10 of the principles that he talks about. We will go through each one of them. Okay, so the first one is maximize the data ink ratio within reason. Okay, so what do you think that means? Yes, okay. So it doesn't restrict you on the amount of ink you can use, but make sure that all the ink that you use has some meaning to it, right? So every ink, okay, so he talks about the traditional print medium, and mostly these days we work with digital display, so it will be pixels, right? So every pixel has a reason for its existence, right? It is not there superfluously, okay? So if you remember some of the comments that I made about your schematic maps, is that there is this very large portion of the screen which is occupied by the title, the sun setting, the beach and the water and all that, right? So in my mind, relative to the importance of the map itself, this is not so important, right? And there is no reason why it should occupy so much of ink, right? So it is disproportionately occupying too much ink for the information that it carries, okay? So there is a rider to that he uses, right? I mean, he does not say that maximize the data to ink ratio full stop, right? He says, comma, within reason, right? I mean, there could be some situations where you might have to use ink for non-information carrying visual elements, right? So you need to know, and then it kind of comes with experience again. With a lot of practice, you know when is the right time to, and how much quantity you use for that, right? So data ink is the non-erasable core of the graphic, the non-redundant ink arranged in response to variations in the numbers represented, right? Any kind of information. It is also the proportion of graphics ink devoted to the non-redundant display of data information. So there is redundant information, non-redundant information. He kind of defines it as that way. So the data to ink ratio, he defines it as the data ink total ink used. Okay. So if it is 1, then it is perfect, right? According to Tufte, that every single pixel that is carries in some information, right? And it is core non-erasable part of the graphic. You cannot do away with it. Okay, I can take out Shweta's beach and then it would still work as a map, right? But you cannot take out important label of a road or a road itself or some iconography used in the map and so on, right? So those are all the non-erasable core of the display, right? So this is a very useful thing. So he kind of points out examples of how some of the graphics suffer from this poor data ink ratio. So this is a bar chart which is displayed in perspective. We already have discussed enough about the problems that perspective causes, right? Because it causes us to correct for it, right? When displayed in a two-dimensional display, okay? Because it is in perspective, we attribute different heights depending on the depth we perceive as being represented, right? So it's all unnecessary, right? And then there is a shadow because it is a three-dimensional pseudo three-dimensional objects that you're creating. You need to also include things like that, otherwise it will look like they're floating in the air, right? So in order to ground them, you need to have the shadow and then the lines and so on, right? So there is a lot of redundant ink here, which compromises the readability of the graphic. That this is a superior alternative, okay, hands down. The same data, but represented like this. I think everything now is non-redundant, and you can see that how superior it is even for reading it, right? In comparison and discrimination, ranking, and all those things, it becomes so much easier. Here, it may not be so, right? It's very difficult to say whether these two yellows are about the same height or by how much they are different and so on. This rule states that the visualization should contain as much data as possible while also using as little pixels as possible. Okay. Now, a lot of people mistake this rule, Tufte, as something that you have to use as minimum as possible, and then they go for this aesthetic called minimalism, right, which is kind of in the vogue right now, and everybody kind of wants to do minimal stuff, and almost they kind of project it as a virtue, right? It is not actually, right? So I have written a short post about minimalism somewhere as a reaction to one of the students' work, because I think a couple of years ago when students are doing, they were all like enamored by this, the aesthetic of minimalism. They were all going for it, and I got sick of it, and then I had to make some response to it, and I made that. I think I will post it to you guys, and it will be worth reading it. It's just 2 paragraphs, short one. Okay, kind of traces the history of how this whole minimalism movement came and how it became, why it became popular, and what are the problems with it. Okay, so that's what I am arguing in that. Through a comprehensive editing and testing process, any visualization can continually be improved upon. So by that, what he means is that you can continue to remove the non-redundant parts of the graphic. So the redundant parts of the graphic.
So where is the note?
Yeah, I actually it's in one of the GitHub threads, right? As a reaction to many of the submissions that I saw. So I'll find it, copy it, and then paste it. So examples of this continuous editing process, right? We saw this example, like how, for example, background ink is this blue. Is that much is necessary? But can you do away with it completely? Can you do away with the guidelines completely? No, we cannot. And then how do you incorporate it and get okay? So you can see that when you arrive at the 4th iteration of the design, it is a much improved version of it, and it has a better data to ink ratio. Okay, simple things like this. So there is a graph which has got this very complex background. Now we are even getting into the gestalt itself, right? Because the background is more prominent than the data points which are supposed to be in the foreground and should be of focus, right? And in fact, the data points are completely lost in this very heavy grid that actually supports reading those dots, right? And here it is completely obscuring them, right? It is having the complete opposite effect, right? So remove that, you know this is what you're supposed to be reading it, and does not mean that this is a better, I mean this is definitely a better display than that, but is this the best display? It needs to go through a few more editing and iterations. So a lot of times we kind of tend to work with existing, backgrounds, existing scales, existing, grids and so on. So every aspect of the visual you need to think about, okay? So if anything is there by default, question it, okay? Maybe the designer of the tool have thought about everything and maybe even put the best default as possible, right? I mean that's what they tried to do, right? So that even somebody who is completely a novice, they just choose the default, they will end up with a decent display, okay? That's a good tool design, right? But then that should not be the case for you guys, right? Because you're supposed to be specialists in the field, right? And eventually become experts in the field, right? You cannot be satisfied with defaults. So when you see any display that kind of exhibits signs of defaults, right, as carryovers from what the tool provides, and most likely it is done by somebody who is very inexperienced, and then you can kind of figure that out easily. In fact, here terms these things as chart junk, okay? So just Google this term, you will find a lot of very serious academic papers written on this subject of chart junk, okay? Chart junk is when you impose a metaphor, okay, in order to fit the theme of the story that the data is displaying, right? Now the first one is a very poor display because it literally reads the text and then translates into the equivalent visual, right? So monstrous costs of how something has been going up from 72 to 80, okay? So that's the monster itself being represented as the teeth of the monster is represented as these bar charts, and it's in some kind of a very weird angle, it is not aligned, the guidelines are going all over the place, it is in perspective, etc., etc. A lot of problems with it. So the core data, the information is here, right? But then you can notice that how insignificant as it has become, in the context of this very prominent metaphor that he is using, right? Or the visual identity that he is using. So I'm kind of always suspicious and not very happy when people try to have these very forced metaphors in graphical display. Sometimes it occurs very naturally, sometimes to evoke certain feelings, even at the cost of information fidelity, you can do that, but then you have to be very careful when you do that, okay? The second one is about how the prices of diamonds have gone up and then it's been falling down. Diamonds were a girl's best friend, and then so the girl is there, and then the profile of the leg becomes the edge of the leg becomes the graph itself. And these are done actually by a very famous designer called Nigel Holmes, right? Again, Google him, you will find it is a British designer, British graphic designer. So this is an example. These are artifacts of defaults, right? A program will by default put some backgrounds, it will put some shadows, it will have some embossing effects and so on and so forth, unless you intervene. So you can see that there is a lot of redundancy here, right? The labels are there, colors are there. I mean, you don't need an extra index there, right? But by default, the program gives you an index, right? And then it reads the value of your data and then creates an index for it, right? And you have to question, right? In this case, is an index required at all, right? Or a legend required at all, okay? So it is not, right? Because it just doesn't make any sense. Okay, second heuristics that Tufte talks about is called mobilize every graphical element to show data, okay? You know, every graphical element is being put to the use of, made to work to display data, okay? The danger of multifunctioning elements is that they tend to generate graphical puzzles with encodings that can be only broken by the designer, right? Some of the very complex visualizations that some of you picked up as examples for your first assignment are so complex that it will require some time to even figure out what is the data and how is it encoded, right? And it requires very complex how to read this chart helps required, right? Most of the work done by Giorgia Lupi, right? The Nobel medals, and some of you guys are doing it for their redesigned replication exercises, right? I think Mahesh is doing one by Giorgia Lupi as well, right? What is the topic?
Visualizing painter's life.
Painter's life, right? He has taken the graphic of Dali's work. But then they are, but very difficult even to, I mean, they are puzzles, but then she's made it easier, but there could be some which are very, very puzzling, right? And so because they are they are multi-dimensional, right? Each graphical element is mobilized to display different dimensionality of a data point, okay? So the size would indicate something, the position would indicate something, the saturation level would, hue would indicate something, the saturation level would indicate something, okay. So you can already see there are 4 data points that one graphical element can be mobilized to do, right? Then it becomes very complex. Thus, design techniques for enhancing graphical clarity in the face of complexity must be developed along with multifunction elements, right? Any reasonably good visualization with a complex set of data, you will have to mobilize every single graphical element to carry multiple variables, right? Then what are the ways by which we can do it? In other words, we should try and make all present graphical elements data encoding elements. We must make every single element effective, right? So one good example of how this is achieved is through a very interesting experiment called the Chernoff faces. These are called the Chernoff faces, right? Now, a face is made up of multiple graphical elements, primitives, right? What are they here in this case? Okay, so the shape of the head, the ears, the eyes, the eyebrows, the nose, and the mouth, for example, right? Now, each of them can be encoded with different dimensions of the data. And what is the advantage of doing it with a symbol like a face? Encoding, say, these elements, right? So 5 data points on these 5 parts of the face is far superior to encoding 5 data elements on one single abstract graphical element, say, such as a square or a rectangle or a triangle. Okay, so that's my claim. Why would that be true? Okay, I mean, we can detect very subtle changes in facial expressions, right? And so therefore, any kind of symbolic representation of the face carries over that sensitivity, right? So for example, no slight changes in the way that your eyebrows change, you can detect and then kind of assign emotions to that person, right? Is this person happy or is not happy? I mean, I don't know what he's thinking at the moment, it's like that. With very familiar people, you are able to do it. We can detect people's mood and emotions with very subtle changes in the facial expressions, right? I mean, there are like million smiles, right? And you can detect very clearly a really happy, heartfelt smile versus something that is very fake, right? And then you look at your selfies, you'll know which are them, right? So that's excellent, okay? So that is one of the reasons why, even though it kind of looks a little bit amateurish, for you guys, there is something in there. Now, Chernoff faces is one of the ways to do it. Now, what you need to do is think of what is it that we are extremely sensitive to, right? What can we detect with the subtlest of the changes and accurately and consistently correctly, okay? So this guy, Chernoff, was actually a mathematician statistician, and he invented, his name is Chernoff, so therefore it is called as Chernoff faces. Display multivariate data in the shape of human face. The individual parts such as the eyes, ears, mouth, and nose represent values of variables by shape, size, placement, and orientation. The key idea is that humans are well trained to recognize faces and discern the smallest of the changes without difficulty. they allow for easy outlier detection, pattern recognition despite multiple dimensions of the data, right. So, if you use an abstract symbol like a square or a triangle or some kind of a shape that you create, right, and then changes to that is very, very difficult, right. You make changes to the height or the shade or something like that, people will not be able to do that. Faces are also emotionally expressive. Okay, so there is somebody who talked about the emotions, right? Who was that? Who said emotion? Yeah. Okay. So there also, suppose your data contains an emotional variable, then it becomes even more easier, right? Even more appropriate also. So metaphorically also you can do it, right? You can also include, because you can, it becomes meaningful as well, right? It's a semantic encoding as well now. Okay, so this is a chart of a data set of 4 by 3, 12 judges from a US Superior Court based on a survey conducted among lawyers who practice in that court. Okay, so these are the 12 judges who are in that court, and I don't know what the questionnaire was and what was the data collected, and then they plotted these 12 judges based on these characteristics, right? And then you could see a face emerging, and this is exactly what they, when they showed the plot to it, they could instantly recognize who this person was. So they hid the labels and then went back to this the sample group which provided the data and tell them, okay, this is a representation of the collective data that we got from you. Now can you recognize who's who, right? And they were surprised to see that there was a very high number of people who got many correct, okay, because of the way it was encoded. You can see that, I mean, even without knowing these judges, you kind of know what these guys are, right? Or who these guys are. So detecting outliers is what said, right? For example, there is, if you say among these things, right, what is the outlier, then the stranger comes through very clearly. I don't know why that guy is a stranger. Okay, it's the only one, right?
The others are below. It's the only one at the top right. As in among the top right.
Okay, so he's the only one among the smiley faces, is it? Is there a person like that?
Just below. Yeah, like where there are two.
Ah, okay. So I don't know what this means. Why is this an outlier, right?
Maybe for this category of.
No, I know, but I mean, just by looking at it, right? I mean, the reason why people are able to detect outliers very quickly is that because their data is encoded like that.
Those similar faces are
At the bottom, okay. So that is one thing I can say, right? Because this kind of this pear-shaped face is these faces, and these faces are all pear-shaped, and this is the only one that is ranks higher, right, on this scale, and then everything else is kind of otherwise fairly distributed. I think maybe that could be the reason. You can see that, I mean. So this is the Giorgio Lupi work, right? Something similar to that. There is here this is not Chernoff faces, but and some abstract encoding. But the designer has gone to a lot of trouble to figure out exactly, and then provided a system of reading it, and also there is an intuitive way to understand it and create a mental model of how each of these graphical components, are read, and therefore they don't have to refer to the legend every time to read it. Okay, so I think this is urban story about I think the top whatever number of cities, right? Top 25 cities or something. I don't know. Among the 25 of the world's most important cities. Okay, 25 most important cities visualized here, and then he writes some. She writes about, like, what are the parameters for this, and then you can see some kind of an encoding happening, right? So this is, I think, let me go to the close-up version of that. Okay, so this one is the okay. height of the buildings, number of inhabitants, then this is the average precipitation. Okay, this is the average price, cost of property, I think, and then the number of visitors, right? The data is encoded along the length, right? Then this is this is actually does not contain, the area contained does not contain any data, but then it would be difficult otherwise to read it. So I think then to tell them that you are supposed to focus on this edge rather than any of the other edges, you can see the gradient fill helps in some way. Okay. So I mean it is a fairly complex encoding, but then it's not something that is too difficult to get it. Okay. Once you get it, probably you will be able to remember it also. Okay. And she does a lot of this type of works, very complex stuff. This is the timeline of the various Pulitzer prizes. Okay, Pulitzer prize is like an Oscar or the Lifetime Achievement Award for architecture, and then these are the various people, and there is a very complex encoding of the types of buildings that these architects built, okay, or known for, and things like that. Okay, so that legend at the bottom tells you about this thing. Okay, it's much more complex in the previous visualization, right? It's almost impossible to remember anything, right? So every single architect, you'll have to go back and refer to this legend to understand it, right? So in this case, a table would have worked much better. Okay, a tabular data of this, from which this data comes from, would have been much more useful and helpful than this this encoding. Okay, so this is an interesting visualization. It's fairly easy to understand once you get it. It's about when famous writers publish their masterpiece, right? How long it took them to do it. For some people, it was the first work that was the masterpiece, but then for some people, it took them very long to write a book that was considered to be the masterpiece, right? And then some people did 2 or 3 masterpieces in their lifetime. Okay, so that data is very interestingly captured. Like at which age they wrote their first book, which age they won acclaim by writing this masterpiece, right? And then so on. So you can look it up, I mean just search for it. All these things are very well documented. Okay, the third one is maximize data density and size and the size of the data matrix within reason. Okay. Now, so if a data is plotted like this, it could end up something like this at the first version of how it is displayed, right? What it does is that it kind of clusters all the data points in one point, so it becomes harder to read. And then while at the same time you also notice that the entire rest of the matrix that supports it is completely useless, right? So changing the scale there so that this part becomes a little bit expanded makes sense, right? So you kind of end up with something like this. So this is the data of the sepal length of flowers, I think, right? Multiple species and or categories of plants, plant flowers. The correlation between sepal length and sepal width. Okay, so how through a series of editing process it could get better. You differentiate a categorical value here and separate them, and then only by color, maybe through shape and color, and finally you end up with something like this, which is a lot more readable, okay, and makes sense, right? You can see that from this display, starting from this display on the left, where it is absolutely kind of completely useless, you have reached a point where it is a lot more useful.